also big grit as well. So I'll share my screen. Let me know when you guys can see it. Okay, you guys can see it?
Yes, it's visible.
Yeah. Okay. Great. So I'll start with what is it that I'm going to discuss about, and what we're trying to build in Entropik Tech, and what is exactly the idea of emotion AI, and how is it different than the usual AI technology that we see all around us, right? And why we are building it, right? So the discussion will mostly like mostly about the state of the AI today, and then uh, you know what are the different technologies that in emotion AI that we have built so far, right? So I'll start with the general idea of artificial intelligence, right? So I think it's been 5 years since the last surge in different algorithms in AI that you guys must have seen, right? So around 2015, we saw like a lot of great papers coming, and a great amount of improvement in computer vision algorithm, NLP, and other algorithms as well, right? So that was a great time for AI, where new algorithms were coming, and the new data was also coming. Better computing platforms were available. Deep learning was also there, right? So something happened then, right? I mean, we started with the idea of that we should also build some sort of an AI, right? Then we started exploring what are the different aspects that we can work on, right? Because AI is a pretty broad term, right? So I'll get to that as well. But the point that I wanted to bring in is that today most of the data scientists are building AI, right? If you look back like 30 years back or 40 years back, it was mostly people from programming language research, or people from logic research, or people from pure mathematics. These were the guys who were building AI, right? But what something happened which is making data scientists to build AI, right? Though the term data scientist, right? I mean, it's not really the people who were initially interested to build AI. Data scientists were more about making sense out of the data, right? So they will take like a statistical data, they will do some sort of inference mining, things like that, right? And that is something that was being done for last 20 years, right? But with the new kind of data which also helps you to build AI, that was a new revolution, right? And that's where we started working on, right? So I'll quickly uh, yeah so when we started, we thought there are different aspects of intelligence, right? I mean, what it means to be intelligent in terms of human beings, and what it means to build intelligent systems for machines as well. So when we look at these intelligence, right, so there are areas of intelligence that we can talk about. So first is that you have perception. So perception means nothing but any species, right, which can take the data from all around it, right? So the environment data that is there available, is it able to take that in, right? So there can be like electromagnetic waves around it, right? Or there can be different kind of sounds, and the different kind of textures, and visual representation of things, right? Am I able to really perceive it, right? Because that's kind of becomes the fundamental input for the intelligence system, right? So we were thinking that we should do something in the perception domain, right? And then there was a chain of thought that we had, right? And I'm gonna take you through that chain, that what was the logic that we had in our mind. So that's why I have actually pointed out like number one, number two, things like that, right? So first is perception, right? You take that data inside, right? And then second is, once you have this data, right, once you have some sort of a understanding of the universe around you, how do you represent the data inside your head, right, in your brain or in your nervous system, right? And that's what is called knowledge representation. Now human beings are significantly different than any machine, the way we actually save the information, right? While in computers it's mostly digital, and a very different format, right? So that was the knowledge representation, right? Once you have this knowledge in your head, you can start doing some sort of a logic and reasoning, right? And logic and reasoning, what I mean is like, if you know that if you have seen in the universe that 2 plus 2 is 4, and that is something that you have actually come up without somebody teaching you the maths, right? That's purely like perception data, and then you doing the logic, right? And then the reasoning is that once you know that 2 plus 2 is 4, you can easily deduce that 4 plus 4 is 8, or 8 plus 8 is 16, or things like that, right? So we as a species have this amazing capability of generalizing our intelligence, right? So once we know a small patterns in the environment, we can easily generalize that easily. Right? Once we can do that, right, then we come to the number four, right, which is the planning aspect. Planning means, that this SPC can now achieve any goal, right? So I, as a person, if I want to, let's say, take the phone and put it on a, put it on charge, right? So I have a plan for it, like that I'm going to pick up the phone, I'm going to take out the charger, put the charge in the socket, and I'm going to connect that to the phone, right? So all of this simulation we can run in our head, right? And that's what makes us intelligence, right? So these were the different aspects that we were thinking, right? So if you see the current, like the earlier wave of deep learning, people were working on these areas, right? Especially if you see the robotics people, they were working on planning systems, like, if a robot has to move from point A to point B with the most amount of efficiency, how will it move, right? And then perception will also be a part of it, like, how do you take that visual data inside? Can you put a small radar on the robot and things like that, right? So all of this kind of makes one agent very intelligent, right? But we were discussing that what is the aspect of the intelligence that has made human beings kind of like the top of the food chain, kind of a species on this planet, right? And then we realized that is actually not just one human being, but mostly the collaborative effort, right? So we can communicate very well, right? If you see the point number five, we have this amazing tendency of communicating, right? And we can actually collaborate through communication, right? And so it's not just one person who is intelligent and who can do the point number one, two, three, four, but it's actually the collaborative effort which actually enables us to be able to achieve great things, right? And that if you solve these aspects, right, within AI, you probably can actually achieve a lot more than actually enabling one system to be smart, right? And when we reached to that conclusion, we started looking at, like I was thinking, I used to think like, what would be, the main key aspect of communication, right? So is it like, developing a new language, or maybe just understanding human languages, right? What enables the technology to be collaborative with human beings, right? Because that's the most important thing that we found, right? Then we realized that it's actually the social intelligence, right? So because just by communication, you cannot probably do a very efficient collaboration, right? At least in terms of human beings, right? We are able to do good collaborations because we can understand each other, we can empathize with each other, right? And we can understand each other's feeling, and we know what actions to take when somebody's feeling something, right? If you don't have that, right, I mean, it would become like, a very robotic communication, which is bound to fail at the end, when we talk about the human beings, right? So if we are targeting human machine collaboration, probably both of them should have social intelligence as well, which is the point number six that I have, right? Both of them should understand each other's feeling and things like that, right? Now machines do not have feeling, right? But they should be able to understand what humans are feeling, right? And what is the behavior of human beings, right? If they look at them, can they come up with some sort of logic that, if they are feeling this, then what should I do, and things like that, right? That sort of computing did not exist before, right? And we were very excited that if we solve that, then I think we can smoothen out the and this is a thought was that I used to like run in my head, that what is the aspect that we should be excited about, when we are building something, right? So this was the sixth point, right? And this is something which is in literature, in computing and computer science research paper, this is usually called affective computing, right? So in MIT Media Lab, this term was coined in 1991 by Rosen Pickett, and she's the scientist there who actually coined the entire term, and also started the field of affective computing as well, right? And yeah, so this is what we started working on. Now I'll just change this. So once we know, right, that this is what we are interested about, we want to make the AI systems which are able to understand human behavior, right? This was the premise of everything that we wanted to do, right? Now the second thing is like, how do you really build AI, right? So there are a couple of things that I've tried to write it down in a very simple language, instead of like using jargon. So you can see, like, the first is the humans will code the logic, right? I mean, I as a data scientist, or I as a computer guy, can code that, if somebody is like feeling sad, and that this is how his face should look like, and this is how the pixel should look like, and then you calculate a couple of things, and then train the AI system, right? It's very hard to do it that way, right? I mean, we quickly realize that you cannot derive code or derive algorithm for each and every part of the intelligence that we possess, right? So let's say I recognize you, right, or I recognize Vajil, right, and somebody tells me that what is the algorithm that I use to recognize him. Probably I'll not be able to tell you, right? So that's very complex, right? So we know that humans coding the logic might not make sense in these cases, right? Then second thing is let machines learn the logic with humans help, right? Which is nothing but is usually called supervised learning in the community, which means that machine is trying to figure out some sort of a pattern. You are just giving tags to it. Right? So let's say again I'm building a facial recognition system, right? And I have 10 faces, right? Machines is trying to do this guy is this guy is this, but before that you actually tell machine that these are the names of the unique faces, right? And then these are the different guys and these are the pictures of them, right? So you kind of assisting the machine to understand, right? Now humans don't do it, right? I mean, if I look at you like 100 times, I will recognize your face, and then one day I'll just ask your name and I'll just remember it, right? So we do it in a very pure, unsupervised manner, right? So that's the third point, which is let machine learn the logic with experience, right? This is something very similar to what the way humans also learn anything, right? So we go out in the world, we understand the environment, right? We keep figuring out different patterns, and then one day we assign names to things, right? And that's how we learn, right? So this is more of an unsupervised learning, right? And then the final thing is artificial general intelligence, right? So as I said, if I go back, right, and if you see uh, yeah, this one, there were different aspects of intelligence, right? And if today any AI system that you see most of the time is targeting one of these, right? And also a small subset of this, right? Not exactly like so if you go to perception, right, there would be deep learning algorithm working on just recognizing faces or maybe just recognizing bottles or something like that, right? So we work in a very narrow area of intelligence, right? But the final frontier for AI is to actually be able to train one AI or maybe just have one system which can actually do all kinds of intelligent things, right? And that's what the final frontier is, right? So as you can see, right, I think we are pretty far from building an AGI system. There are a couple of companies who are actually targeting that, right? But most of the time in the industry, when you are guys are working with the clients or in the product, you will not see like AGI applications pretty soon, right? So this is what we also decide that we probably will go with supervised plus unsupervised kind of learning, and we will try to build these empathetic and emotion AI systems, right? The third is how do we assess, right? So once we build these systems, right, how do we know that how good my system is, right? So let's say I build an AI which can play tic-tac-toe, right? How do I know that it's a good AI or bad AI, right? And what is possible? What is the potential? Like, I mean, what is the kind of like a big complexity or for building these systems, right? So we wanted to assess that, right? And that's where we encountered something like this. What you're seeing on the screen is there are like five different aspects, right? Five different kind of levels of how AI is good. So the first one is the optimal, right? Which means you cannot build systems better than that. I mean, that the system has achieved like the most intelligent state, right? Which is a tic-tac-toe or Rubik's cube. If you see, like, I mean, you will see like many examples like that which are optimal, right? So people have kind of coded the algorithm and it's almost solved, right? So it's almost impossible to beat the AI, or maybe even if it is, right, it will probably get you a draw or something like that, right? So that's the optimal AI, right? Now the second is superhuman, right? Which we say that it has not achieved the best so far, right? This AI system, but it's still better than human beings, right? So right, and it's better than almost every human being. It's not just like maybe better than most human beings, but almost every human being, right? So we achieve those kind of accuracy in Scrabble, chess, Go. These, so Go is a recent addition in this, right? So if you see in that table, right, I mean, this was DeepMind, I think, who actually came up with a new system which can play Go, and then it actually beat almost every human being that it was playing with, right? Then you have high human, which is like it is almost comparable to human being, but something like, but still better than most of the human beings, right? So that means kind of like it only experts can beat it, right? So that's like Dota, and the system was released by OpenAI, right? So these are the systems which are like maybe if you're an expert, maybe probably you can beat them, maybe you are more accurate, otherwise they'll be more accurate, right? Then you have par human, right, which is almost as a human being, right? So which is like one example is image classification, which is the way you recognize a couple of things, maybe other human beings will also do it, and then machines can also do it, right? So it's like neck to neck kind of a comparison there, right? And then you have at the end subhuman beings, right, which is subhuman AI, which is AI is not as good as human beings today, right? So let's say a face recognition system, right? I mean, the way we recognize faces is much more efficient than AI, right? AI needs to be trained on a lot more data with a lot more supervision, then only it can maybe, and with a very narrow field is when we can actually make these systems as good as human being. Otherwise, mostly they fail, right? So you must have experienced that when you're talking to a Google AI or maybe an Alexa, right? It fails many times because in the speech recognition and stock market prediction and things like that, right? So we wanted to know where would we be, right? We thought that probably we will end up in subhuman category because probably we'll not be able to recognize human emotion as well as another other human beings can do it, right? So this was one of the initial understanding that but when we are building, how do we assess, right? So this assessment is very subjective than something like cross validation, something like accuracy score, which is like more data sciencey way of assessing your goodness of your algorithms, right? But this is more of like where do you land in terms of the whole picture of the building AI system, right? One interesting thing is if you see the top three, right, the optimal AI, subhuman AI, and high human AI, right? These most of these are games, right? I mean, almost all of them are games or puzzles, right? And there's a reason for it, right? The reason is that games have limited, limited combination of possibilities, right? So games are not infinite, right? So any game will be always be bounded by some sort of a constraint that these are the possibilities that the game can have, right? And depending on the game, that can be huge or that can be less, like for something like chess it can be huge, right? But the number of possibility for a game of tic-tac-toe is like pretty small, right? So when you have a limited set of possibilities, right, it's actually a little easier for you to build an AI which can explore these possibilities, because AI has much faster computation now, right, than humans, and then take a decision on that, right? So that's why you will see, like any company or any research papers who are coming up with an AI and claiming that it's much better than human beings is most likely to be a game or most likely to be a system which has a very less number of combinations, right? But let's say face recognition, right? This is like endless. This is infinite, right? Not just because there are 7 billion faces in the world, but also that those faces can exist in multiple ways, right? So if I'm looking at like this, right, and then I do this, like I mean, just turn my face, that's a different visual cue, right? If I look up, that's a different visual cue, right? So a single face can also come up with huge amount of possibilities, and then add light to it, right? I mean, put different lights on my face, then again, good great amount of variation there as well, right? So when the possibilities are huge, it becomes a little harder for us to kind of build the AI systems which are good as human beings, right? So again, just a second. Yeah. So so emotion, yeah, now coming to what we are building, right? So this was more about discussion on what AI is, and what got us inspired to build an emotion AI system. Now when we talk about emotion AI, there are two ways people understand it, right? One is that people immediately think that AI is able to now feel anything, right? Which is not correct, and which is also not making any sense, right? There's no point of making AI to feel anything, right? All you need to know, or all you need to do is that AI should be able to feel others, like AI should be able to know others emotion. It might not feel it, there's nothing as like feeling in the AI machines or anything like that, right? But it should be able to understand what you are feeling, right? And that's the most important thing, right? So there were a couple of efforts before these artificial intelligence systems came. People used to use EEG and GSR sensor, right, which is also one of the sensors that we also use, right? So if you see the second point and the sub point in that, the first sub point says the sensors in the invasive technologies, right? So you put a couple of sensors around your head, on your face, and on your fingers, right? And you try to get the physiological data from it, right? And then you can calculate what somebody's feeling, right? That's something that we experimented with the very I think in the early 1.5 years, we also used to do that, right? If you go to like an extreme of that, then you have companies like Neuralink, right, where they are trying to put a small sensors or a small sensors inside your head so that they can detect the data right from the neuron, right? And that possibly can translate into they understanding your feelings and thoughts and other things, right? Which is very invasive, right? But if you think about intelligent system, right, this is more of a sensor and calculation and things like that. But humans don't do it like that. If I am able to understand what you're feeling, and whether you're happy or sad, I'm just able to do it just by looking at your face, listening to your voice, and possibly, like, just looking at the overall postures, right? So we wanted to build something like that, right, instead of putting sensors around you, right? So that's the second point, where you see, like, using perceptions like human beings. So things like speed, gesture, face, and words. So in that line, we experimented around 12, 13 different technologies, right? I have listed four of them here, because these are the ones which we are actively selling and actively, you know, building products on top of them as well, right? So the first technology is facial coding, where we actually try to understand the different expressions on your face, and then kind of calculate what you might be feeling, right? The second is brainwave mapping, where we actually take data from your brain. We put a small EEG sensor on your head, and we try to get that voltage data and then convert that into some sort of a cognitive measurement. Right. Third is eye tracking, which is also very important in behavior understanding, right? Because if I also know that where you are looking at, right, that kind of gives me a lot more hint on what you might be feeling and why you might be feeling it, right? If I'm looking at a movie, let's say, right, and I build an AI system which can actually take your face and understand that. If I also know that this guy was looking at the actor's face or an actress face, right, and then only he was feeling certain emotion, then my analysis of that data becomes much more richer, right? So that's why we built an eye tracker. And the fourth thing is speech analysis, right? So there are multiple cases where you might be speaking something, and I can take that cues, take that audio data in, and then use that to understand what you might be feeling, right? So these are the four technologies which we are, like, actively, selling and building product on. And I'm going to talk about the first and the third one, right, because of lack of time. I'm going to talk about facial coding and eye tracking. If anybody is interested in understanding how we did brainwave mapping, what we do in speech analysis, what we are planning to do going forward, please feel free to reach out to me. I'll share a couple of contacts also at the end of the session as well. Yeah. So facial coding, right? So what is facial coding basically? So first biggest problem that we had was understanding that, you can actually understand good amount of emotion from faces, right? To do that, we studied a literature by Paul Ekman, right? And Dr. Paul Ekman is the kind of pioneer in understanding faces. He has, like, huge amount of literature and great amount of, I think, 30 and 40 years of research on the same topic. The biggest thing that he found out was, like, these facial expressions are universal, right? So if I'm smiling, right, and I'm pulling my lip corners up, this is actually smile, and this is actually happiness all over the world, right? Unless somebody's faking it, right? So the immediate impulses which actually takes you to do a smile is always mostly about the happiness, right? And similar to that, most of these expressions that you do were actually found out to be universal. So that means, like, if the way I look sad here in India will be the similar way I will look sad in US as well, right? And this is the reason why we are able to watch Western movies and Western series as well, right? If imagine, like, if they had very different facial expressions and very different way of expressing emotions, right? Then probably we would have, like, very hard time understanding their series and anything like that, right? So this is how what inspired us, because this is something universal. So if you solve for one, then probably we have solved for everything, right? So we can actually take that solution and go global as well, right? So what you're seeing on the on the screen is, like, how do we calculate, right? So in the top right corner, you'll see, like, these AU numbers, right? So AU 1, 2, and a couple of numbers might be missing, right? Each of these numbers is actually defining a small event on your face, right? Whether your nose went up or your chin went up or whatever happened, right? Or your lip was pulled up, right? Anything like that, right? So each of these units are assigned a code, right? And then the combination of those codes, which you can see in the bottom left side, right? So that's a happiness, right? So happiness is a combination of code number 6 and 12, right? So this is the initial understanding of, like, how you can build these kind of system, right? So if you can understand these codes, or if you can actually figure out what these action units are, then you can actually derive what emotion somebody might be feeling, right? And you can also derive the intensity of that emotion as well, right? So let's say how we do it in computer vision, right? So I think this might require, like, a lot more time to explain everything, but I'm going to glance through to it, right? So firstly, we just need to detect a face, right, in front of the camera, right? The second is we need to detect the landmarks, right, which is the key facial element on your face, right? So there are if somebody's building, like if one of you guys get interested and try to build it, right, there are a couple of open source solutions available to it, right? We train our own systems because we want more accuracy, right? And we have our own kind of data set, and we also have, like, our own improvements also in these algorithms, right? But this would ideally look almost the same, right? So you will detect the faces and the nose and eyes where they are, right? And then based on that, you can kind of crop the elements which you need, and then do all the analysis that I showed in the previous slide. And then you can come up with something like, what's the third point? You can get the emotions, right? If you see the last couple of emotions, which are attention and engagement, I'm going to talk about it later, so you can kind of ignore that right now. Yeah, so some issues faced by us, right? These were biggest challenges that we faced, right? And I think when you guys will be building AI and practically doing something to build product, or doing real-time AI systems, I think you will face a lot of these challenges what we felt, right? And I think this would probably help you guys to figure out what to do next, right? So one of the challenge was the pure pose of the face, right? I mean, your face can be in any of, like, how do you say, like, the orientation can be anything, right? So somebody might be looking frontal, somebody might be doing a side profile view, right? And these are different faces, and your AI has to learn everything, right? And that becomes very hard, right? So first set of algorithms that we built, we actually asked the users to look frontal, right? Because we knew that we cannot handle a lot of variation, right? So that was one of the problems. Like, the second problem was occlusions, right? So you might be keeping, you know some hand on your face, or maybe some mask, which is the new thing that came up right after we built a couple of AI systems, right? And then third is the light, right? And this is the I think the most notorious one, right? So because you can't really do much about light, right? So if somebody's sitting in the dark, it's very hard to figure out what he's feeling, because enough light is not on his face, right? There were a couple of innovation that we have done in terms of, like, doing pixel processing and how to really enhance what we're trying to sense, right? So if you see, like, I'm not really interested into every pixel in your face, right? I'm just interested in a couple of pixels which can give me the motion data, right? So there are ways where you can enhance those pixels even if the light is not that great. So these are a couple of things that we tried there, right? And then you have, like, beard and other things, right? So which is again a different kind of occlusion. It's a constant occlusion, right? So a hand is like a partial occlusion where somebody will keep hand on your face and then they will take it out as well. But this is something that will probably going to be there all the time, because the beard is always there, right? So we built a system called Affective, right, where we put a small website, and with all these images that we had collected over years, and we would ask users to tag it, right? And then we will do all these different variations also, right? So this is very different than building AI on your academic data, right? Because academic data is mostly very clean, right? And it's very nice, but the real data looks really ugly, right? And you can't do much about it, right? You can't really filter them out, right? So your AI system has to see all these variations, right? So that means we decided that we will go more complex in building these algorithms, and also more complex in terms of the variation in the data. So if you see, someone can come in this website and start tagging that what he's feeling, that somebody else might be feeling, right? Now the biggest challenge here is the confusion, right? So emotions are very subjective. So if I'm sad, somebody might think that I'm sad, right? While the other guy might think just, yeah, this might be neutral face, right? I mean, it's not really looking sad. And then somebody else might be thinking that, he's actually looking like an angry guy, right, instead of sad, right? So there's always this confusion that we saw, right, which is unusual, because when we are tagging and doing AI system, let's say object detection, always a phone is a phone, right? A bottle is a bottle, right? So there's no such confusion in image classification or object detection. But in this case, this was the biggest confusion, that the tag itself was not decided, right? The tag itself had doubts. So to solve that, we use something called inter-rater reliability, which is like, we vote on the tag, right? And multiple people with different backgrounds will vote on that, right? And only when some tag crosses like 70-80% of the votes, then only we accept that as a valid tag. Otherwise, we invalidate that, right? So that strategy kind of helped us a lot in terms of, like, building a better model, right? So this is how the solution looks like today. I mean, if you have like a multi-phase or a single phase, any kind of a system where the different phases are there and they're visibly like good, I mean the faces are not like completely not visible, then we'll be able to detect some emotion on that, right? So this is like a video, somebody doing like the way we are doing this Zoom calls, is something similar where we are detecting emotion for everybody, right? And then if you see, interesting thing here is like we also track people, right? So if you see on each box, there's like person one, person two, person three, things like that. And we do all this analysis on that, and then we generate a report or anything like that, right? So you can think like be it in a meeting, or be somebody watching a video, somebody browsing website, anywhere the face can be visible, anywhere where a webcam can be turned on, we can actually detect emotions there, right? Now, just one interesting thing, just by looking at the emotion might not give you a great understanding of what happened in the session, right? How was the meeting, or maybe how was the session when people actually watched the movie, or how did they like the website, right? So we need to derive some metrics on top of these emotions as well, right? So some of these metrics are, the two of them is attention and engagement. If you go to our website, you probably will see a lot more which are now added, but attention is something where we focus on whether you were paying attention where you're looking at it, not right. So people doing Zoom calls to teach students, right? They might be very interested into doing this thing, right? Engagement is again a combination of emotions which we feel is adding up to engagement, right? So let's say I was watching a YouTube video and my camera was turned on. Can I detect whether somebody felt engaged with the content or not, right? Or the content just like just went through and he did not really do anything about it, right? So engagement always correlates with they doing some action also, right? So if high users will high engagement will probably have a lot more possibility of liking that video or maybe sharing it, right? Users with less engagement will not have that kind of probability. So that is something that correlates pretty well. Now talking about facial coding, let's talk about eye tracking, right? So facial coding was something that that tells you about the human behavior, right? About what he's feeling, whether he's feeling engaged or not, whether he's feeling happy or positive or negative, anything like that, right? Which is what the earlier premise was like when we started. But then we were also interested that if we also know what they were looking at on the screen, right? Because all these algorithms that I'm talking about, all of them run on a website or on a phone, right? So on a desktop, right? So these are the machines that we are using, right? We have not really experimented with a lot of edge devices so far, right? So mostly these are the two form factors that we have, right? So most of the time people are browsing something, most of the time people are watching something or reading some content, right? It would be interesting to know what they're looking at, right? So that's why we started building an eye tracking. Now eye tracking, the problem statement is I just want to predict where you are looking at, right? Whether you're looking at the icon or the logo or the actor, this is what I wanted, right? The second challenge is it should be able to support different kind of light and pose, right? Which is the earlier problem that we also discussed in the facial coding side, right? So that's what I'm again and again saying, right? Any AI system that you build and you want to deploy it in a real production system, you probably have to be very kind of maniac about the data, right? That the data should have all kinds of possibilities, all kinds of variable variations, because uh, nothing beats that, right? I mean, no amount of complexity of the algorithm, no amount of research will beat the power of data in that case, right? So if you have like good data to start with, I think that's what you should do in the first place, right? Now the third is to be able to run these algorithms on users machine, right? Now this is very interesting, right? Because we are doing this emotion AI, so a lot of time people will talk about privacy. People will talk about that, I might not be able to come, might not be able to share my video, right? I might not be comfortable sharing my face or anything like that, right? So it's a genuine problem, right? And when you build these systems in practical sense, you cannot really rely them to give this video to you, right? One of the ideas like you give a pop-up and ask for the permission, right? But that just doesn't work for everybody, right? Some of them will say no and you can't get their data, right? What the biggest thing that we did was to take all these Python algorithms, right, which we built, and we wrap it in a C++ code, right? So now there is a team in the company which is like converting all these algorithms into C++ system, right? Now C++ native code can actually run right on your browser and also in mobile phones, be it Android or iOS, because that's how like all of them support native applications. So this was an interesting thing that we did. So now all of our algorithms are converted into an SDK or some sort of library which can run right on your laptop or your phone, right? Which I consider is as one of the biggest achievement, as big as being able to actually detect these things, right? So as we tried for the accuracy improvement, we also tried for being able to run everything on mobile phones, right? That does many things for us, right? One is that it solves the performance challenges because you get a lot of computing on the client machine itself, right? Rather than you taking all these videos and then relying on the server to actually batch process all of this, right? The second thing is the speed, right? I mean, if you're doing different server calls, it's probably going to be very slow, right? But if you're running it right there, every inference gets interpreted much faster, and the data is sent to the phone, so it's sent to the server. And then you have the privacy concern, which is gone completely, right? Because there's no face or nothing at all that we are sending to the server, right? We are just sending the emotion data, which makes no sense. I mean, in the sense, like, which is not identifiable, right? I mean, you cannot identify a person by looking at somebody felt happy at this moment, right? So these are the 3 4 challenges that we had. So we solved it by using this SDK, right? Now, what is the algorithmic challenges, right, in terms of building an eye tracker? First is, so if you search eye trackers in Google, right, and when we start building it, you will always end up seeing some sort of a um, uh, some sort of a hardware, right? And that hardware would be like a small strip most of the time, which you can place on your laptop or mobile phone. And what it does is, like, it has an IR sensor, right? So it sends the infrared wave right in your eyes, and the reflection of it gets recorded, right? So it's very accurate, right? So if you see the second image, the first image is just a camera image. The second image is the coming from IR sensor, right? And you can see how accurately it can predict, or it can know where the pupil center is, right? So and once you know the pupil center, everything else becomes very easy, right? Because you probably can do some sort of a calculation and figure out where somebody is looking at, right? But the input that we get, right, with the webcams and especially from the webcam in the laptops, right, is the third picture, right? You can see how hard it becomes for us to really understand what is there in the eye, right? Because most of these cameras are not high resolution, right? So the eye patch is even smaller, right? And the guy, somebody might be sitting pretty back, right? So in that sense, like, the eyes might just get 15 16 pixels, right? So it's very hard to figure out and build algorithms on top of that, right? So, but still, that was the challenge that we took, right? And we said we want to solve it, right? So the reason why we said we will solve it that way, right? Because clearly you can see the second image is amazing, right? I mean, anybody would like to build algorithms on top of it, right? But there were practical reasons why we chose software based, right? So just for the understanding of the words, so if you're using an IR sensor or any laser sensor, that's not hardware eye tracker, hardware based eye tracker. If you're using just a webcam, which is already embedded in your laptop or mobile phone, that's usually called a software based eye tracker, right? So this was the initial analysis that we did, right? Clearly, in many aspects, the hardware eye tracker is better, right? You can see the accuracy, right? That's the first, right? You can be pixel precise, almost pixel precise. So you can actually predict what somebody is reading, right? What line he's reading. So you can be as accurate as a small area, right? Which is not possible by software eye trackers today, right? So that was one place where hardwares were better, right? And also the speed, right? So the hardware-based eye trackers can predict at 60 hertz, right? Which is pretty fast, right? But we did the practical analysis. We said, okay, if I'm if I'm just having errors less than 200 or 100 pixels, I probably can analyze most of the things on the video, right? I can understand where people were looking at, what area they were looking at, what face they were looking at. If there is a logo is mostly more than 50 100 pixels, right? So we are not really missing on a lot of information, right? The second thing is also the speed, right? Which is see a human being can only perceive like at around 15 16 fps. After that, it's like your brain is just making things up and then just kind of adding those frames, right? So going beyond 60 hertz or even 30 hertz did not make sense, right? So today our algorithm at natively, what you are seeing on the screen is like 14 to 20 hertz, but we have now reached around 30 35 hertz as well, right? So now it's like much better, right? So in terms of accuracy, we also solved it one more way, right? Apart from being just 100 pixel, having just 100 pixel error, we also have a huge amount of scale, which is the last point that you can see. The last point says that you can run multiple parallel session on software-based eye tracker. So today, if you want to test your creative or test your website or do anything, anybody's eye tracking, you can probably do it for thousands of people in within 5 minutes in our platform, right? Because we are completely hardware software based, right? If you have a hardware based, that means you shipping those hardwares to hundreds of people, they installing it, you see the last second last point is the installation, right, where they install the driver for it and then they figure it out, right? And not every user can be well versed in doing that, right? So all of these challenges we solved, right? We said we will have scale, we will have speed, and we will also have like zero installation. And the only thing that we have is like, we might be a little less accurate than the hardware based eye tracker, but that also we solved by the power of data, which is right, that most of these companies which had a hardware eye tracker, they just ran sessions on 30 people, right? But we were able to do it on 100, 200 people, right? When you have 200, 300 people data, right, you can remove the outliers and get much richer into understanding of the data than just having 30 people, right? And that's where we kind of beat what hardware eye trackers were, right? So yeah, so this is why we chosen hard software eye tracker, right? Now I'll come to the solution, like how did we solve it, right? Just like facial coding, right? So when you're building these algorithms, there's a very high level understanding of these algorithms, right? So first point is you might want to calculate these geometrical features, right? Might want to calculate where my nose is, and when direction from my nose to my screen, and then get angles from my eyes, and then might want to do some tan theta, something like that, the high school geometry, and then figure out where I might be looking at. Right? That's the very intuitive way of actually solving it, right? Which is also in line with what I explained earlier, which is like you coding the entire logic, right? So this was one effort that we also did. But the second was like why don't we train the machine to understand all this logic, right? And instead of me doing trigonometry, can I make machines do all that automatically, right? So that's why we said, okay, that's the second point, right? We're using eye patch as an input, right? So I just pass my eye, I don't do anything, right? I just say this is the eye, and you have to figure out where somebody's looking at, right? And you have to train yourself, right? So this was an initial thing that we did, and it was successful. It was much better than the first idea that we had. The third idea that we are still working on is that apart from just giving one eye, can I pass like different kinds of eye? Can I pass different kinds of pose and light and all kinds of possibility? Similar way that we discussed about the facial query, right? Where we collected millions of data to cover off all kinds of possibility, right? Because as I said, I always believe that if you have enough data and all kinds of variation, that's always better than any other algorithm, right? Because you can do much more with that, right? So this is something that we are trying to do now, right? Uh, but we made the machines understand the entire eye mapping, right? So this is how the algorithm works now, right? We have a face image, we get the eye crop. It's a simple, just like I explained in facial coding, right? And then there's a CNN algorithm, which is like we built it in house. This is just not just simple CNN. It's like a combination of different types of CNNs, and then we kind of bridge them together, and they take different inputs and all that. And then we all user has to, which is the first point, is it has to calibrate the eye tracker with the 14 points, right? And then the only limitation today that we have, right? So as you see, right, the third point that we are working on right now, once that gets solved, maybe the second constraint will go. So the second constraint, we can predict as accurate results as long as user space is steady, right? So you don't have to move your face a lot, right? As once I'm doing your eye tracking, right? Now you might be thinking that this is a big constraint, right? But the practical thing is the kind of media that we get, or kind of websites that we get, it's always about 1 minute, 2 minutes, right? So mostly users are able to be steady and do the test, right? Also, in terms of competition, it's like you will find it this kind of constraint in almost all the eye trackers in the world, right? So there's no single eye tracker that claims that you don't have to, like, you can move around and then still will be able to do your eye tracking, right? So this is an active problem, active research problem that people are working on, where they want to make the eye tracker completely, uh, completely free of all kinds of variation, right? Which is a huge problem if it gets solved, right? So with this, you see the third point, which is like we were able to reach 15, 20 FPS with on the client machine. Today, that has become around 30 FPS also, right? So because we use a small tracker, it does all these calculations much faster. So yeah, so this is how our solution looks like, just like the facial coding looked like. This thing will ask you to look at these dots, right? So the moment you open your phone, and if our product, which is Affect Lab, if it is installed, it can actually try to show you a couple of dots, right? So it's trying to learn the mapping from your eyes to your camera, right? Sorry, to your screen, right? So and you see the numbers are decreasing, as it kind of gives you a user a sense that I'm kind of completing my test, right? So once you have these couple of dots and you look at them, right? This time the machine learning algorithm is understanding everything. It's trying to figure out that mapping from your eyes to the screen. And once you do that, so let's say after point one, and then you have a center point. This is the last point. And after that, we also calculate. So as a data science, you guys might have done like cross validation and things like that, right? We do something different, right? It's kind of a cross validation, but it doesn't take like 80-20 split kind of thing. It's actually on all the data sets, but it's actually adding a variation and noise to that, right? So we do all that analysis, right? And we calculate how accurately we have learned your mapping, right? So this guy got a 5 star, right? The video that I showed, right? If you get 3 star or 2 star, then we actually recommend you to do the test again so that we can learn your mapping, right? So the possible cases for the machine not being able to learn your mapping might be because of bad lighting, right? Or maybe the half of the face is like completely white because of the huge amount of light, right? Or maybe completely dark light, or maybe your eyes are closed, right? Or maybe you are at a certain angle where your eyes are just not visible, right? So you're way below the camera field of view, right? And those things are there, right? So apart from this, we also correct that for users, right? So what it means to give the right input. So we show them that this is how you should sit, and our computer vision system helps them to figure out that you are too far, you are too close, you're too above the green box and things like that. So this is what we do, and once you do this, then anything that you watch, we'll be able to track your eyes, right? Now, how do we interpret that data, right? So this is the interesting thing, right? This is the kind of like a meat portion of the discussion on eye tracking, right? So users are not interested in understanding everything about the screen, right? So let's say I'm a video creator, or I'm a website creator, or I'm like a product owner, right? Who is testing his product using these eye tracking and facial coding technologies, right? I'm not interested in everything. I'm interested in a couple of statements, right? Like, am I better than my competition, right? So if I put my logo versus competitor logo, what do people notice more, right? Second thing is whether people are noticing something or not, right? How much they are noticing it, right? How long it takes to notice it, right? So if you see, these are the four metrics that I've pointed out. One is the average first discovery, which kind of tells you that out of all the users that who have seen the media, how long it takes for user to notice what you are interested in, right? And what somebody is interested in is usually called area of interest, which is AOI, right? As the heading of the slide is, right? So on that AOI, we calculate all these four things, right? The second point is earned attention, which is like out of all the attention given to all the medias, how much attention this particular AOI got, right? The percentage of people watched means like out of 100 people, how many people really noticed it? Maybe some of the people just completely missed that, right? And the percentage was like total exposure time and how much time was devoted to that media by people, right? So maybe people were like, oh, if they were noticing your logo all the time, that's something good, right? So maybe the logo was exposed to 5 seconds to 10 people, which means the total exposure will be 5 into 10, and let's say which is 50, and you got the exposure of 40, which is a good case, right? That kind of tells you that most of the people are noticing for most of the time, right? So that's a great news for your logo, right? So if you see a small point there in the end is we recommend to test with around 30 people, right? So as I said, our eye tracking actually using a lot of power of data, right? So more and more people will watch it, so more and more people, like, we will be able to refine our results, right? We'll be able to figure out the outliers. We'll be able to like kind of um, give more exposure to so what is important and what is the visible field looking like, right? So how does the data look like visibly? We also did a visual plot of all this, right? So this is how the data looks visibly, right? So there's this image of ship and where people are noticing, right? So here people like noticing the bottom, and right, maybe because of some they ignored it completely. Maybe they noticed some other media which was below it, right? So this is just the crop of the ship, right? So you have a heat map, you have a transparency map. One interesting plot is gaze plot, right? So which is the third point, right? And which might be very exciting for people who are more into data visualization kind of a field, where we also show um, uh, the chronology of your vision or your gaze, right? So it's a sequential data. So where you actually say that first you looked at the dot one, and then you moved to dot two, and then you moved to dot three, right? Because once you analyze this for multiple users, right, you kind of know the gaze pattern on this image, right? And then you might be able to put the logo or put the interesting things in the right part, right? Which is the very exciting thing, right? Which is what many clients have done after looking at this, right? So this is again a great idea, right? And yeah, just to notice, while we are doing all this, we are also doing facial coding, right? So you also get to know when he was looking at point 6, how was he feeling, right? So all of this together becomes like a really nice story for users, right? So now I'll come to the use cases, right? So as I said, like I've just discussed about two technologies, right? Might not be able to cover all four which we have for in 1 hour, but yeah. So these are the different the things that we do, right? Now the use cases, right? I mean, when we are building, like I discuss very academically, right? What it means to build AI and then emotion AI, right? But can we really use this somewhere, right? So the first is consumer research, right? For digital and physical products, right? So and mostly digital, right? So digital products are like UX, your softwares, your media, your videos, almost most of the things on your laptop or phone, right, can be categorized as a digital product, right? And you can test that using all these technologies. You can see that where people look at, how people respond to it, whether people are liking it or not, right? So there are different products that we have built on top of it. One is called Affect Lab, one is called Affect UX, right? So all of this information you'll find in our website, and we're launching more and more products as well, right? So this was like pure kind of B2B business that we built on top of it, which is like doing really well. So this kind of gave us an understanding that yes, this thing actually is useful as well. Right? So building emotion AI is not just like an academic pursuit, but is also like it can be an economical pursuit as well, right? Now, the second thing is which we don't work on, but it's a great use case for emotion AI, and I know a couple of companies and a couple of friends who are working on it. Is the empathetic AI assistants, right? So today AI assistants like Google Assistant and Siri and Alexa, these guys are able to understand you in terms of like what you're saying and the commands, right? But what if they are also able to understand what you're feeling, right, and how angry you are or how happy you are? Maybe they'll be able to do much better, right? I'm not really able to find it, like give you the exact use case, but that would be much more interesting to see in the future, right? And the technologies that we are building on voice and brainwave, maybe all of that can help in these aspects as well, right? And the third one, which is interestingly, I found 1 year back, like by discussing a couple of companies, the management of mental health, which is like it's actually able to, like it's actually possible to see visual cues on your face and especially your voice to understand somebody's mental health, right? And if you track that user for a long time, right, so it's not, it might not be possible by just by looking at you I can say that you might be feeling anxiety or depression. But if you're tracking somebody for a long time, if you understand his history, right, then you can kind of correlate these things, right? It's actually able to figure out that this guy used to be like happy go lucky, and then now he's like he's feeling low, and it might be early signs of depression or anxiety, right? And then there are other ways of actually tracking it. There are the tests which you can conduct right on the platform to do that, right? So we don't work on this actively, but yes, I this is a very very interesting use case which can kind of revolutionize the mental health aspect in the healthcare industry as well. So these are the use cases that we are so the first use case is that what we are working on so far. And yeah, that's pretty much what I had to discuss about the different technologies and what we are building in emotion AI. I would love to take any questions that you guys have, and also will be sharing my so we're sharing my contact in case you guys are interested in working with us, or maybe have any discussion, any queries, anything like that. Feel free to reach out to me.
Wow. Thank you so much, Sumit, for a great session. So we are open for questions. If anybody would like to, you can unmute your mic and ask, or if not, then you can write in the chat box as well. So, Sumit, till the time people will think, I'm just
Yeah.
asking, so you can, you'll, if somebody wants that knowledgeable presentation that you describe all the categories.
Mhm.
So if anybody want that, so are you able to share that, or like these are the company content?
um Probably cannot say right now because I did not think about it, right? But I think I should be able to share it. Just let me get back to people in the company, right?
Yeah.
Because there's nothing sensitive content so far on this slide, so maybe I should be able to share it right now. I'll share it with you, and then you can forward it to people.
Sure. So actually, two people ask in the chat box the same question that
Sure,
we need that thing. So
sure,
that's why I'm asking.
sure. I'll do that.
Hello.
Hey,
Yeah, so how accurate are we in the emotion detection? Like, is there some matrix or something that we are using to calculate the accuracy and all?
okay, great. So I'll tell you on this problem. So we are very accurate in, like, I mean, in terms of, so there are two ways of measuring the accuracy, right? One is, you do that cross validation, and then you do some sort of a test and validation set, and you do calculation on that. In that regard, we are mostly 97, 98% accurate on most of the emotions, almost all of the emotions, right? But that's, the problem with that approach is, like, it's mostly, um, it depends on the data, right? So you can only be as accurate as the data you are comparing it on, right? So the second approach that we take usually is compare ourselves with, again, all the vendors within the world, right? So the giants in the emotion AI space, like Affective, Google, Azure, Microsoft, right? So we are as good as them, and we are even much better in some of the emotions than any of these vendors, right? So that's how I will put it. Like, I mean, we kind of lie in the top, top vendors in terms of the emotion accuracy level, right? So we were able to, like, beat many of these vendors in many competition and different deals, in terms of accuracy as well. But yeah, in terms of cross validation, it's mostly 97 to 98% for different emotions.
And how are you like using the eye tracking and emotion together? Like, I
Okay.
want to know the use
Yeah.
case for that.
Yeah. So let's say, so I'll point out one of the use case, right? So let's say you are launching a promo, right? So promo for a small TV soap, right, that you created. So you have a TV soap which runs every day, and you are launching a new promo, right? And then you have like two, three different promos for it, right? Your creative team comes up with two, three different promos, and it says that, should we campaign with the promo one or promo two or promo three, right? So then what you do is, and what people want is, like, what people will tell us is that they want people to focus on, the actor's death, maybe something like that is event is happening, right? And that's what is getting people excited to watch that show, right? So they'll create that, and they'll test it with our platform, right? And they'll look at, how many people actually notice the key element around that event, right? Whether the actor, whether the mom crying and things like that. That's one. And then whether they felt sad or happy or engaged at least, right? So this is where you will actually get the facial data as well, and also the eye tracker as well, right? The creative which will do the best in terms of all, measuring all this, for all the three creatives, will be the one which people will like to see more, right? So that's how we use it. So this is one of the use cases, right? There can be a number of use cases where we like to, bridge all these data. Sometimes people use eye tracking and facial coding, and also and brainwave, right? And put the data together. So there can be different use cases, and we have an insight teams and the sales team which actually guides people to sometimes you just need a eye tracker, right? You might not need facial coding, but you might want to use combinations as well. So yeah, there can be multiple use cases.
So we have one more question in the chat box.
Okay. So for some reason I am not able to see, just a second. Okay, I can now. Okay, can using hardware objects such as IoT sensors lead to a better accuracy than just using AI/ML? Okay, great question. So we have tried that once, right? So we partnered with Intel, and we tried to put our algorithms in IoT devices, right? Because of the some of the use cases, let's say retail use cases, right, where people are actually roaming around and buying something, and maybe the store is interested into understanding their emotions as well, right? So today there's no such thing as like it will lead to a better or bad accuracy, right? It's almost the same, right? But there can be some use cases where accuracy can be low, right? So let's say you have a very constrained hardware, right? Something like a mobidius stick or something like a very small computing device, right? What we have to do in that case is, like, we convert our algorithms and the models and everything to a smaller form factor, right? So to a smaller size as well, right? Which might sometimes end up in, like, compromising the accuracy, right? But which is something that we have not seen so far, right? But so far there's no difference whether you are running it on this machine or that machine. Even on we ran it on Google Chrome, right? And this is not a great environment for running AI algorithms, right? Because the Chrome is not optimized for it, right? But we were able to run our algorithms on Google Chrome native application engine, and we were able to deliver the similar results as well, right? So not so much, but yeah, theoretically, if there is a very small constraint device, if you are not run any algorithm, I think that's true for any AI where you might want to have some compromise with the accuracy. Yeah.
So anyone have any more questions? This is the last call for Q&A session. If anybody have the questions, please let us know.
Or in case you guys are like shy, you
Yeah,
can just send those queries to this email ID as well, right? So yeah.
yeah. So no problem. You can write an email to sir as well, and whenever you get the time, definitely you'll get a reply for that. So no problem, Mr. Chauhan. Thank you for the beautiful session and the
Thank you so
knowledgeable
much.
session.
Yeah.
And thanks again from the team from the Bitrate to deliver this session and giving time for us. Have a great day. Have a great weekend to
Have a great
everyone and
weekend.
to you.
Yeah.
Thank you so
Thank you so
much.
much, guys. Thank you so much. Bye bye.
Bye bye.